Section. Introduction. We're going to talk about how diffusion models have transformed the way we generate images. These models have brought about a new level of realism and diversity in image generation, with a stable training process. However, they have a downside. The process of creating an image from noise is slow and iterative, requiring many expensive neural network evaluations. This makes it difficult to use these models interactively as a creative tool. To speed up this process, previous methods have tried to simplify the noise-to-image mapping process into a single step. But this is a complex task and can be quite demanding. One of the challenges is the high cost of running the full denoising process just to calculate one loss computation of the simplified model. Recent methods have tried to overcome this by gradually increasing the sampling distance of the simplified model, without running the full denoising sequence of the original diffusion. However, these simplified models still don't perform as well as the original multi-step diffusion model. In our work, we take a different approach. Instead of trying to match the noise and diffusion-generated images, we aim to make the images generated by the simplified model look indistinguishable from those generated by the original diffusion model. Our goal is similar to other generative models that aim to match distributions, such as GMMN or GANs. However, scaling up these models for general text-to-image data has been challenging. To overcome this, we start with a diffusion model that is already trained on large-scale text-to-image data. We then fine-tune this model to learn not only the data distribution, but also the fake distribution produced by our simplified generator. Since diffusion models are known to approximate the score functions on diffused distributions, we can interpret the denoised diffusion outputs as gradient directions for making an image more realistic or more fake. We then update the generator based on the difference between these two, pushing the synthetic images towards higher realism and lower fakeness. Previous work has shown that modeling the real and fake distributions with a pre-trained diffusion model is also effective for optimizing 3D objects at test time. We believe that a similar approach can be used to train an entire generative model. We also find that pre-computing a modest number of the multi-step diffusion sampling outcomes and enforcing a simple regression loss with respect to our one-step generation serves as an effective regularizer in the presence of the distribution matching loss. Our method draws upon inspiration and insights from VSD, GANs, and PIX2PIX, showing that by modeling real and fake distributions with diffusion models and using a simple regression loss to match the multi-step diffusion outputs, we can train a one-step generative model with high fidelity. We evaluate models trained with our Distribution Matching Distillation procedure, DMD, across various tasks, including image generation on CIFAR10 and ImageNet 64x64, and zero-shot text-to-image generation on MS COCO 512 by 512. On all benchmarks, our one-step generator significantly outperforms all published few-steps diffusion methods. On ImageNet, DMD reaches FIDs of 2.62, an improvement of 2.4 times over consistency model. Using the same denoiser architecture as Stable Diffusion, DMD achieves a competitive FID of 11.49 on MS COCO 2014-30K. Our evaluations show that the images generated by our model closely resemble the quality of those generated by the costly Stable Diffusion model. Importantly, our approach maintains this level of image fidelity while achieving a 100 times reduction in neural network evaluations. This efficiency allows DMD to generate 512 by 512 images at a rate of 20 fps when utilizing FP16 inference, opening up a wide range of possibilities for interactive applications. Diffusion models have emerged as a powerful generative modeling framework, achieving unparalleled success in diverse domains such as image generation, audio synthesis, and video generation. These models operate by progressively transforming noise into coherent structures through a reverse diffusion process. Despite state-of-the-art results, the inherently iterative procedure of diffusion models entails a high and often prohibitive computational cost for real-time applications. Our work builds upon leading diffusion models and introduces a simple distillation pipeline that reduces the multi-step generative process to a single forward pass. Our method is universally applicable to any diffusion model with deterministic sampling. Accelerating the inference process of diffusion models has been a key focus in the field, leading to the development of two types of approaches. The first type advances fast diffusion samplers, which can dramatically reduce the number of sampling steps required by pre-trained diffusion models, from 1,000 down to merely 20 to 50. However, a further reduction in steps often results in a catastrophic decrease in performance. Alternatively, diffusion distillation has emerged as a promising avenue for further boosting speed. They framed diffusion distillation as knowledge distillation, where a simplified model is trained to distill the multi-step outputs of the original diffusion model into a single step. However, a significant challenge is the expensive cost of running the full denoising trajectory for each realization of the loss function. To address this issue, some methods train a series of simplified models that have the number of sampling steps of the previous model. In contrast, our method shows that the simple approach of pre-computing the diffusion outputs is sufficient, once we introduce distribution matching as the training objective. Section Summary. Diffusion models have been successful in generating realistic images, but their slow sampling process limits interactivity. Previous methods have tried to accelerate sampling by distilling the noise to image mapping into a single-pass student network, but the performance still lags behind the original model. In this work, we propose a distribution matching distillation procedure that trains a one-step generative model by modeling real and fake distributions with a pre-trained diffusion model, achieving high-fidelity image generation with a significant reduction in computational cost. Section. Distribution matching. In recent times, certain types of generative models have been successful in handling complex datasets by restoring samples that have been distorted by a specific mechanism, such as noise injection or token masking. However, there are also generative methods that don't focus on sample reconstruction as their training goal. Instead, they aim to match the synthetic and target samples at a distribution level, like GMMD or GANs. GANs, in particular, have demonstrated exceptional quality and realism, especially when the GAN loss is combined with task-specific, auxiliary regression losses to reduce training instability. This has been applied in various areas, from paired image translation to unpaired image editing. However, GANs are not commonly used for text-guided synthesis, as careful architectural design is required to ensure training stability on a large scale. Recently, several studies have drawn parallels between score-based models and distribution matching. Specifically, Prolific Dreamer introduced variational score distillation, VSD, which uses a pre-trained text-to-image diffusion model as a distribution matching loss. Since VSD can use a large pre-trained model for unpaired settings, it has shown impressive results in particle-based optimization for text-conditioned 3D synthesis. Our method refines and extends VSD for training a deep generative neural network for distilling diffusion models. Additionally, inspired by the success of GANs in image translation, we enhance the stability of training with a regression loss. As a result, our method successfully achieves high realism on a complex dataset like LAION. Our approach differs from recent works that combine GANs with diffusion, as our formulation is not based on GANs. Our method shares motivation with concurrent works that use the VSD objective to train a generator, but we specialize the method for diffusion distillation by introducing regression loss and demonstrating state-of-the-art results for text-to-image tasks. Our goal is to distill a given pre-trained diffusion denoiser, the base model, into a fast, one-step, image generator that produces high-quality images without the costly iterative sampling procedure. While we aim to produce samples from the same distribution, we don't necessarily seek to reproduce the exact mapping. We refer to the outputs of the distilled model as fake, as opposed to the real images from the training distribution. We train the fast generator by minimizing the sum of two losses, a distribution matching objective, whose gradient update can be expressed as the difference of two score functions, and a regression loss that encourages the generator to match the large-scale structure of the base model's output on a fixed dataset of noise image pairs. Importantly, we use two diffusion denoisers to model the score functions of the real and fake distributions, respectively, perturbed with Gaussian noise of various magnitudes. Our distillation procedure assumes a pre-trained diffusion model is given. Diffusion models are trained to reverse a Gaussian diffusion process that progressively adds noise to a sample from a real data distribution, turning it into white noise over a certain number of time steps. Starting from a Gaussian sample, the model iteratively denoises a running noisy estimate, conditioned on the time step, or noise level, to produce a sample of the target data distribution. Diffusion models typically require multiple steps to produce realistic images. Our one-step generator has the architecture of the base diffusion denoiser but without time conditioning. We initialize its parameters with the base model before training. Ideally, we would like our fast generator to produce samples that are indistinguishable from real images. To achieve this, we minimize the Kullback-Leibler (KL) divergence between the real and fake image distributions. Computing the probability densities to estimate this loss is generally intractable, but we only need the gradient with respect to the generator parameters to train our generator by gradient descent. Taking the gradient of the KL divergence with respect to the generator parameters, we get the scores of the respective distributions. Intuitively, the score of the real distribution moves the sample toward the modes of the real distribution, and the negative score of the fake distribution spreads them apart. Computing this gradient is still challenging for two reasons. First, the scores diverge for samples with low probability. In particular, the real distribution vanishes for fake samples. And second, our intended tool for estimating score, namely the diffusion models, only provides scores of the diffused distribution. To address these issues, we perturb the data distribution with random Gaussian noise of varying standard deviations, creating a family of blurred distributions that are fully supported over the ambient space, and therefore overlap, so that the gradient is well defined. We then show that a trained diffusion model approximates the score function of the diffused distribution. Accordingly, our strategy is to use a pair of diffusion denoisers to model the scores of the real and fake distributions after Gaussian diffusion. The real distribution is fixed, corresponding to the training images of the base diffusion model, so we model its score using a fixed copy of the pre-trained diffusion model. However, as the distribution of our generated samples changes throughout training, we dynamically adjust the fake diffusion model to track these changes. Our final approximate distribution matching gradient is obtained by replacing the exact score with those defined by the two diffusion models on the perturbed samples and taking the expectation over the diffusion time steps. Here, we add a time-dependent scalar weight to improve the training dynamics. We design the weighting factor to normalize the gradient's magnitude across different noise levels. Specifically, we compute the mean absolute error across spatial and channel dimensions between the denoised image and the input. In the next section, we show that this weighting outperforms previous designs. Section Summary. Recently, generative models have been successful in scaling up to complex datasets by recovering corrupted samples using predefined mechanisms. While GANs have shown high realism in image translation tasks, they are less popular for text-guided synthesis due to training instability. Our method extends variational score distillation, VSD, for training a deep generative neural network by combining distribution matching and regression losses, achieving state-of-the-art results for text-to-image tasks. We use diffusion models to approximate the score functions of the real and fake distributions, and our training procedure includes a classifier-free guidance. Section: Regression Loss and Final Objective. We're going to discuss the regression loss and the final objective of our model. In the previous section, we introduced a method for matching the distribution of our generated samples to a target distribution. This method works well when the generated samples are heavily distorted by noise. However, when the noise level is low, our method can become unreliable. This is because the probability of the real samples can approach zero. Moreover, the score we use, which is based on the gradient of the logarithm of the probability, doesn't change when we scale the probability density function. This can lead to a problem known as mode collapse, where the fake distribution assigns a higher overall density to a subset of the modes. To prevent this, we add a regression loss to our model to ensure all modes are preserved. This regression loss measures the distance between the outputs of the generator and the base diffusion model, given the same input noise. We create a dataset of random Gaussian noise images and their corresponding outputs, which we obtain by sampling the pre-trained diffusion model using a deterministic ordinary differential equation solver. In our experiments with CIFAR10 and ImageNet, we use the Hune solver from EDM, with 18 steps for CIFAR10 and 256 steps for ImageNet. For the LAION experiments, we use the PNDM solver with 50 sampling steps. We find that even a small number of noise image pairs, generated using less than 1% of the training compute, acts as an effective regularizer. Our regression loss is calculated using the Learned Perceptual Image Patch Similarity, LPIPS, as the distance function. The final objective of our model is to train the network with the denoising loss, which is used to help calculate the gradient of the KL divergence. For training the generator, the final objective is the sum of the KL divergence and the regression loss, multiplied by a regularization parameter of 0.25. We apply the two losses to distinct data streams, unpaired fake samples for the distribution matching gradient and paired examples for the regression loss. We also use classifier-free guidance to improve the image quality of text-to-image diffusion models. We generate the corresponding noise output pairs by sampling from the guided model to construct the dataset needed for the regression loss. When computing the distribution matching gradient, we substitute the real score with that derived from the mean prediction of the guided model. We assess the capabilities of our approach using several benchmarks, including class conditional generation on CIFAR10 and ImageNet. We use the Frechet inception distance, FID, to measure image quality and clip score to evaluate text-to-image alignment. Our distribution matching distillation substantially outperforms competing distillation methods with identical base diffusion models. We also perform detailed ablation studies verifying the effectiveness of our proposed modules. In one phase, we train a text-to-image model on the LAION aesthetic -6.25 plus dataset with a classifier-free guidance scale of 3. We show that our distilled model achieves an FID comparable to the original model, while offering a 30 times speed up. Finally, we train another text-to-image model on LAION aesthetic -6 plus, utilizing a higher guidance value of 8. This model is tailored to enhance visual quality rather than optimize the FID metric. Our models trained with our distribution matching distillation procedure can produce high-quality images rivaling stable diffusion. We train our model on class-conditional ImageNet 64x64 and benchmark its performance with competing methods. Our model surpasses established GANs like Big GAN Deep and recent diffusion distillation methods, achieving a near-identical FID score compared to the original diffusion model, while also attaining a 512-fold increase in speed. On CIFAR10, our class-conditional model reaches a competitive FID of 2.66. Section Summary. The authors introduce an additional regression loss to address the unreliability of the distribution matching objective for small amounts of noise and to prevent mode collapse in the optimization process. They use a paired dataset of random Gaussian noise images and corresponding outputs from a pre-trained diffusion model to measure the pointwise distance between the generator and base diffusion model outputs. The final objective is to train the generator using the distribution matching gradient and the regression loss, with additional details provided in the appendix. The effectiveness of their approach is demonstrated through experiments on CIFAR10, ImageNet, and class-conditional image generation benchmarks, where their method outperforms competing distillation methods in terms of image quality and speed. Section: Ablation Studies. Let's delve into the studies we conducted to test our method. We started by comparing our approach with two basic models, one that didn't include the distribution matching objective and another that didn't incorporate the regression loss in our framework. The results are summarized in the table on the left. When we removed the distribution matching loss, the basic model generated images that lacked authenticity and structural coherence, as shown in the top part of the figure. Similarly, when we excluded the regression loss, it led to unstable training and a tendency for mode collapse, which resulted in less diverse generated images. This problem is depicted in the bottom part of the figure. The table on the right shows the benefits of our proposed sample weighting strategy. We compared it with two popular weighting schemes used by Fusion and Prolific Dreamer, which are represented as sigma_t divided by alpha_t and the cube of sigma_t divided by alpha_t. Our strategy improved the FID score by a significant 0.9 as it normalized the gradient magnitudes across noise levels and stabilized the optimization process. Next, we evaluated our model's performance for generating images from text using the zero-shot MS-COCO. We trained a text-to-image model by distilling Stable Diffusion version 1.5 on the LAION aesthetics -6.25 plus dataset. We used a guidance scale of 3, which gave the best FID for the base Stable Diffusion model. The training took about 36 hours on a cluster of 72 A100 GPS. When we compared our model with the latest approaches, our method outperformed style GAN-T and surpassed all other diffusion acceleration methods, including advanced diffusion solvers and diffusion distillation techniques like latent consistency models, UFO-Gen, and InstaFlow. We significantly narrowed the gap between distilled and base models, getting within 2.7 FID from Stable Diffusion version 1.5, while running about 30 times faster. With FP16 inference, our model can generate images at 20 frames per second, making it suitable for interactive applications. For generating images from text, diffusion models usually work with a high guidance scale to improve image quality. To test our distillation method in this high guidance scale regime, we trained another text-to-image model. This model distilled SD version 1.5 using a guidance scale of 8 on the LAION aesthetics-6 plus dataset. Our approach outperformed various diffusion acceleration methods, even those using a 4-step sampling process, as shown in the table. Qualitative comparisons with competing approaches and the base diffusion model are shown in the figure. However, our method has some limitations. There's a slight quality difference between our 1-step model and finer discretizations of the diffusion sampling path, such as those with 100 or 1000 neural network evaluations. Although the impact on quality is minimal considering the significant speed gains, it suggests there's room for further improvements in efficient 1-step generative models. Also, our model's performance is inherently limited by the capabilities of the teacher model. Like the limitations observed in Stable Diffusion version 1.5, our 1-step generator has difficulty rendering legible text and detailed depictions of small faces and people. We expect that distilling more advanced models, like SDXL, could lead to significant improvements. Our model uses a fixed guidance scale during training. Introducing a variable guidance scale option, similar to the conditional guidance approach used in guided distillation, could give users more flexibility in image generation during inference. We started this work while Tai was an intern at Adobe Research. We're thankful for the insightful discussions with Yilan Xu, Wangxuan Xiao, and Mingyat Kong. This work is supported by the NSF Award 2,001,519 and 1,955,864, and Singapore DSTA under DST 00 OECI 203000823, New Representations for Vision.